Charge, electricity, and magnetism. Charge. Charge is the technical term used to indicate that an object has been prepared so as to participate in electrical forces. This is to be distinguished from the common usage in which the term is used indiscriminately for anything electrical. For example, although we speak colloquially of charging a battery, we may easily verify that a battery has no charge in the technical sense. Example, it does not exert any electrical force on a piece of paper that has been prepared as described in the previous section, which I didn't read, although I read it. Two types of charge. We can easily collect reams of data on electrical forces between different substances that have been charged in different ways. We find, for example, that cat fur prepared by rubbing against a rabbit fur will attract glass that has been rubbed on silk. How can we make any sense of all this information? A vast simplification is achieved by noting that there are really only two types of charge. Suppose we pick cat fur rubbed on rabbit fur as a representative of type A, and glass rubbed on silk for type B. We now find that there is no type C. Any object electrified by any method is either A-like, attracting things, A attracts and repelling those it repels, or B-like, displaying the same attractions and repulsions as B. The two types A and B always display opposite interactions. If A displays an attraction with some charged object, then B is guaranteed to undergo repulsion with it, and vice versa. The Coulomb. Although there are two types of charge, each type can come in different amounts. The metric unit of charge is the Coulomb, rhymes with droulon, defined as follows. 1 Coulomb is defined as the amount of charge such that a force of 9 times 10, a little more technical, see the drawing, occurs between two point-like objects with charges of 1 c separated by a distance of 1 meter. The notation for an amount of charge is Q. The numerical factor in the definition is historical in origin and is not worth memorizing. The definition is stated for point-like, i.e. very small objects, because otherwise different parts of them would be at different distances from each other. A model of two types of charged particles. Experiments show that all the methods of rubbing or otherwise charging objects involve two objects, and both of them end up getting charged. If one object acquires a certain amount of one type of charge, then the other ends up with an equal amount of the other type. Various interpretations of this are possible, but the simplest is that the basic building blocks of matter come in two flavors, one with each type of charge. Rubbing objects together results in the transfer of some of these particles from one object to the other. In this model, an object that has not been electrically prepared may actually possess a great deal of both types of charge, but the amounts are equal and they are distributed in the same way throughout it. Since type A repels anything that type B attracts and vice versa, the object will make a total force of 0 on any other object. The rest of this chapter fleshes out this model and discusses how these mysterious particles can be understood as being internal parts of atoms. Use of positive and negative signs for charge. Because the two types of charge tend to cancel out each other's forces, it makes sense to label them using positive and negative signs, and to discuss the total charge of an object. It is entirely arbitrary which type of charge to call negative and which to call positive. Benjamin Franklin decided to describe the one we've been calling A as negative, but it really doesn't matter as long as everyone is consistent with everyone else. An object with a total charge of 0, equal amounts of both types, is referred to as electrically neutral. Self-check. in style with the text here, criticize the following statement. There are two types of charge, attractive and repulsive. And I can think about that later. Coulombs Law. A large body of experimental observations can be summarized as follows. And as I get going here, I'm going to omit the explanation of the actual equation. Coulombs Law. The magnitude of the force acting between point-like charged objects at a center-to-center distance, r, is given by the equation where the constant k equals 9 times 10. You can see the force is attractive if the charges are of different signs, and repulsive if they have the same sign. I think it would be helpful if I actually watched some separate videos on Coulombs Law. Clever modern techniques have allowed the 1 over r squared form of Coulomb's law to be tested to incredible accuracies, showing that the exponent is in the range from 1.9 to 2. Again, see the text. Note that Coulomb's law is closely analogous to Newton's law of gravity, where the magnitude of the force is, well, you can see, except that there's only one type of mass, not two, and gravitational forces are never repulsive. Because of this close analogy between the two types of forces, we can recycle a great deal of our knowledge of gravitational forces. For instance, there is an electrical equivalent of the shell theorem. The electrical forces exerted externally by a uniformly charged spherical shell are the same as if all the charge was concentrated at its center, and the forces exerted internally are zero.